Today's topic is network transfer speeds and miscellaneous data storage.
Let's go back and talk about our file sizes back here. Obviously, we came up with a file size. We might have come up with something that was 31 kilobytes as being our theoretical file size on the disk. If you actually open something and save it as a JPEG file, chances are, and then on any operating system, you can get info about the file. You can actually find out how big it is on the disk. Nearly always the file size on the disk will be less than what we've calculated. All our calculations that we're doing for this unit, for our file sizes, so our picture file size or our audio file size, all those things are what we call the theoretical file size. They're almost never the actual file size, just because your operating system or your algorithm that you're using to save the file has compression. So we do need to talk about compression a little bit. There are two types of compression: lossy and lossless compression. Essentially, your computer has lots of tricks for shrinking the file size. And there's two different ways of doing it. First one we're going to talk about is lossy compression. These are basically ways of losing non-critical information. Non-critical information is something that's determined by the computer to be information that humans don't need. So, for example, if you're listening to an MP3 file or some audio that has been compressed using lossy compression, chances are it means that it's not recording information that is outside of a human's hearing range. So there's no need to record really high frequency sounds if the humans can't hear it. There's no need to record really low bass notes if the humans can't hear it. So by just dropping off that information, we've saved some file size. Now, when we're developing this algorithm, we can set our threshold. We can say, well, how much compression do we want? And ideally, you want a large amount of compression that's unnoticeable to the human. But if we set our compression algorithm to not sensitive enough, then it will probably trim off. It'll be trying to trim off the top range that humans can't hear, but it might trim too much, and thus you're going to get a weird sound in the headphones. I'm not sure if you've ever listened to a highly compressed MP3, but it sounds weird at the high end. Hi-hats on the drums and various other high frequency noises sound with this really washed out digital sound. You'll also lose lots of bass notes, which you might not notice if you're just listening to it on a normal stereo, but if you're playing it through a big PA system that's got really big speakers, then you'll notice that playing a heavily compressed MP3, you don't get the same low range. So again, the computer's doing its best to try and lose information that humans won't notice. But if we set it to lose too much information, if we want really heavy compression, then you will notice it. So that's audio. Those things are called compression artifacts. Compression artifacts are anything that after we've compressed something, if the human, that's listening to it or watching it or observing can see that it's digital, can see that it's got pictures that aren't quite right or sounds that aren't quite right, then that's what we call a compression artifact. This is called lossy. The really most important thing here is that once a file is compressed with lossy format, we cannot get it back in another way. If I've got a really high quality audio, but I need to send it to you through a slow internet connection, I can create it as an MP3. I can compress it down to something that's quite small, like a few meg. I can send it to you. You can listen to it in its compressed form. You've got no way of uncompressing it back to its original. You've got no way of getting all the data that I had at my end before I compressed it. So audio compression artifacts I've talked about. Here's an example of some picture compression artifacts. It should be probably clearer on your notebook, in your textbook, than it will be on the screen here. But this is where we've got some JPEG artifacts. If we have a look at the balloon around the edges here, you can see some really weird boxes of colors. This is an artifact of JPEG compression. Also, even in black and white text, if you zoom in on this extract, from Wikipedia, it's just black and white text, but you can see a lot of this weird grey lines about it. Those are JPEG artifacts. And essentially, that's what happens when we set our compression too high, or when our compression just can't do what we need it to do in terms of avoiding some sort of evidence that it's been digital compression. You might think, why on earth would these grey boxes be a compression artifact? If we're trying to get maximum compression, how come it would add extra colours in? And the answer is JPEG is an incredibly complex compression algorithm, and the way it works is all algorithmic based, and you don't really have to understand it. But trust me, that it's compressing this in a way that means that when it uncompresses, it can store that information easier and smaller if it adds those gray boxes in. So adding those gray boxes in essentially means it can store this as a very, very small file. There's some list of other compression formats here. So things, often there's a really common link between a compression algorithm and the file type that we put it in. So if you're saving it as a JPEG file, for example, then that is defining what sort of compression algorithm it's using. So we've got JPEG and GIF are picture files, MP3 and MP4 are video, sorry, MP3 is audio files, MP4 is a video file. They're all using a compression algorithm that is defined in the file type. We've also got OGG and AAC as audio files as well. Now, there's another type of compression as well that we call lossless compression. You've probably seen a lot of this if you've heard of anyone using a zip file. If you want to, if I say, can you put that into a zip file and send it to me? That's using lossless compression. It's essentially not looking at all at the content. Now, let's think about what JPEG's doing. JPEG is actually reasonably intelligently going, oh, you've got a bunch of blue up here. In the original picture, they're all about the same blue. So I'm going to save some space by just calling it all the same blue. So really, there'd be thousands and thousands of pixels there. If we store every single one of them as a 24-bit color, then that's going to be a lot of data space. But rather, we can just say, well, let's not store 24 bits for all of them. Let's store 24 bits for one of them and say, okay, every single pixel in this box is that 24-bit color. So we've just saved some space. What it's doing is it's looking at the content and intelligently working out what can be compressed, what information can be lost, and what can't. Lossless compression doesn't really look at the contents of the file. It doesn't look at the whether things are blue or red. It doesn't look at whether sounds are high-pitched that might not be heard by humans or anything else. All it really does is look at the file as a string of zeros and ones, because every file can be stored as a string of zeros and ones, and say, can we store this more efficiently? And there are ways, different algorithms do different things. So zip is one type, RAR is another. There's a whole bunch of different compression file formats. And each one will say, well, I could store this as a string of, let's know that our files are going to alternate. So we've got zeros and ones and zeros and ones. If I store this as a 1, 1, and sorry, no, I won't go into too much detail. You don't need to know how these algorithms work at all, apart from that they can take a string of zeros and ones and store it in a smaller string. So that one might somehow compress to that, which given by some algorithm, we can then uncompress into that. Now, the advantage of this is that if I can compress something using a lossless format into something like that, it'll be smaller. I can send it to someone. They can then decompress it and get the original file perfectly. The disadvantage is that we might have compressed something like a JPEG picture into this format. This format is obviously not JPEG anymore, so I can't just open it in Photoshop or open it in anything that can open JPEG files. I need to decompress it first. So I need to double click on the zip file. That'll create the JPEG on the hard drive. It's important to note that any file can be compressed. As I say, all the zip or the RAR does is look at a string of zeros. So it can be a Word document, a file, like a JPEG, an MPEG, or any other sort of document, Word document, anything, absolutely anything can be compressed and put into a zip folder. The advantage of lossless compression is that anything can be done with it. I can make something smaller and send it to someone. But the disadvantage is it can't be used. It's not in a usable format in that way at all. Someone at the other end has to decompress it. Obviously, it wouldn't make any sense to use lossy compression this way, because if it didn't recompress the original perfectly, it might, if it misses an occasional 0 or an occasional 1, that might sound like it's not catastrophic, but it would make it completely unreadable. So if you've got a JPEG file and you just randomly cut out a 0, then any JPEG won't be able to open the file at all, and you get really weird, strange artifacts that makes the file completely unreadable. If you just cut out a single bit from a Word document, it doesn't mean that you're just missing the E here or that F becomes a G, but rather Microsoft Word will just go, no, I can't read this file at all. The information's not correct. So we need to make sure if you are compressing it using lossless compression, it does so. You need to make sure that if you are using lossless compression, you have a way for me to zip it and for the other person to unzip it, because without that, it's just going to be useless. So that, if anything I've said doesn't make sense, you can certainly spend some time reading through those notes there. I'm going to make a point here as well that you're not going to get asked any technical questions about compression. Nowhere will you be asked to say, this is compressed with a JPEG that gets 80% compression rate, what's the new file size, or how do things compare? You'll just get asked for a general discussion of what's the difference between lossless and lossy, what are appropriate things to compress with lossless, what are appropriate to compress with lossy, and what are some inappropriate files for lossy. Something like a Word document, you couldn't use lossy compression on. It doesn't make any sense. Yeah, that's right, Hugo. Hugo just asked a question about corrupted files. And yes, if you do try and open a Word document and it says this file has been corrupted, what it basically means is that somewhere in its long string of ones and zeros, something doesn't make sense. Maybe it's missing a bit, or something else has gone wrong. Somewhere, somehow, a 0 has changed to a 1 where it hasn't supposed to be. And Microsoft Word just doesn't know how to handle that. All right. Finally, this is the last part of this little unit, and indeed the last part of the unit that we're looking at completely. I think we've just got, so this is the last topic I'm going to be talking about, and then you can do all these questions for understanding. This is actually the end of the unit. So for the rest of today's lesson and all of tomorrow, I'm just going to give you time to do revision, answering these questions for understanding. Do I need to worry about those? Yeah, no, that's not going to work, Hugo. There's not an easy way around it. I'll talk to you about it a bit later if you want. We will move on though. All right, so far we've been talking about file sizes and how to convert between kilobits and gigabytes and whatever else. The final little extra complication in those sorts of questions that you might need to address are one of transfer speeds as well. So you might get asked questions about network speed. For example, if we've got a 1 megabyte file and it takes 2 minutes, to get there, what's the speed of our transfer? Now, just like physics and any other science you've done, speed is equal to the size divided by time. That's not given to you in any formula sheet, but it's easy enough to remember. And so all you're really doing is a whole bunch of speed is equal to size over time calculations. But remembering that it can get tricky because you might have your speed in one unit size, like megabytes, and your size in a different size, like kilobits. So you're going to have to do appropriate conversions there. So let's have a look at this. If example 1, find the speed of a file transfer if a 1 megabyte file takes 2 minutes. Give your answer in kilobits per second. Well, first of all, turning things into bits makes sense. So let's just do our 1 meg conversion into bits, which gives us that value there. That's the same sort of thing we've talked about previously. And then our number of bits divided by a second, since we're entering in bits per second, let's turn that into seconds. If that was bits per minute, then we'd change our question a little bit. But divided by 120 gives us this many bits per second, which we can then convert and get 69.9 kilobits per second. So again, earlier I talked about how we might have a different unknown. This next example is another unknown. We're still using our speed is equal to size. We're still using our speed is equal to size over time. But in this case, if we are told the size and we're told the speed, then we're going to need to work out the time. And so that just means we can rearrange this to easily be time is equal to size over speed. And then we can work out, okay, so the amount of time it takes is just the size divided by the speed. Let's make sure our size and our speed are the same units. So we'll get everything into bits and bits per second. And in this case, we're turning 3.25 gig using the same method we've talked about previously. Turn that into how many bits is that? Our speed is 25 megabits per second, which we can write in that. And so I'm going to do that. So I'm going to do my size, which is, let me just change the color here. So I'm going to do that thing, which is our size in bits, divided by that thing, which is our speed in bits per second. And we get an answer of that many seconds, which I can then turn into minutes fairly easily. So I'm quickly going through these examples because after I finish talking, I'm just going to give you time to work through them. But there's certainly some examples there you can work through. Have a go at some of those questions for understanding when I finish talking. Now, there will be, we've just finished the unit officially. There's not more things that I need to talk about, apart from just the idea that you're going to get questions in this topic that you haven't seen before. A really big part of this, especially in A standard questions, a really big part of this unit is, here's a completely new system that describes what sort of, some sort of application that we need. You have to work out the file size. And it just gives you something new. So there's an example here I just want to work through that tells us Service Tasmania needs a new database for tracking vehicle registrations. The system stores one letter as ASCII, then a two-digit number, then two-digit ASCII. That's a typical number plate. So for example, we might have a number that is a number plate that is a letter, and then two numbers, and then two letters. That's a number plate of some car out there in Tassie. If we want to store that information, how many bits are required to store each possible vehicle registration? If we've got 400,000 bits in the data, 400,000 vehicles in the database, what's the total size in megabytes? Now, maybe as well, for some other application, we might be storing a picture with each particular vehicle registration as well. Like we might be storing a picture of the local, of the owner, in which case we might also say, and we've got a picture here that's like 200 pixels by 200 pixels, and we're going to need 400,000 of them. So you're sort of combining a lot of your knowledge from different parts of the unit in file sizes into one. So to work on this actual problem here, let's not worry about the picture. Let's do the question as given. We have three characters which take 25 bits each. So that, which take 7 bits each, because there's 7 bits per ASCII character. So that bit there is 21 characters. We've got digits that can represent a number from 00 up to 900, up to 99. How many bits do we do that? Well, we know that 7 bits will get us to 128, since 2 to the 7 is 128. So that's going to be far enough. Essentially, the important thing here to remember is that 2 to the n, where n is our number of bits, gives us how many records that we can store. And often we need to know n is our number of bits. So if we need to count numbers up to 128, we're going to need 7 bits to do so. That's a really common calculation you're going to need. So in this case, we're going to need 7 bits. So we had 21 to store our characters. We need 7 bits to store our 2-digit numbers. That means we've got 28 bits per record. So 28 bits per record times by 400,000 records gives us, and the calculation continues on the next, no, the calculation doesn't continue on the next page, whoops, it's there. That gives us 11,200,000 bits to store our database, and then we can convert that. So again, the maths isn't important here. What's important is that you're seeing an example of a fairly typical A standard question, which might be, here's a completely new situation. You haven't seen this situation before, but can you break it down into what are the information requirements in the situation and turn it into bits and bytes? There's another example there that I'm not going to go through, but you can read that in your own time. I suggest that's what you do when I stop talking. There's some questions for understanding that you can have a crack at as well. And then we finish the unit in our textbook. We're now on to sample exam questions.